Hey everyone, and welcome. Today we're tackling a classic problem in abstract algebra. We're given a ring R and an ideal I, and we need to find all the prime ideals of R that contain I. Let's jump right into the problem statement. Problem. Let R equals x where f equals x to the fourth minus x cubed plus x squared minus 2x plus 4. Let I equal 3R, the principal ideal of R generated by 3. Find all prime ideals P of R that contain I. Give generators for each P. This looks a little intimidating, but the key insight is to simplify the problem. The prime ideals of R containing I are the same as the prime ideals of the quotient ring R modulo I. Our first step is to figure out what R modulo 1 looks like. Step 1. Simplify the ring. Let's analyze R over I. Remember, R equals zx modulo f and I equals 3R. So we're looking at the quotient ring. R over I equals zx modulo f divided by 3 times zx modulo f. Using the third isomorphism theorem, we can simplify this expression. It's isomorphic to zx modulo 3 in f. Now we can apply another standard trick. The isomorphism zx modulo 3 is isomorphic to z3x, the ring of polynomials with coefficients in z3. This gives us a much simpler ring to work with. R over I is isomorphic to z3x modulo f bar, where f bar is our original polynomial f with all its coefficients reduced modulo 3. Our new, much simpler goal is to find the prime ideals of this ring. Now for the fun part, let's take our polynomial f and reduce its coefficients modulo 3. F equals x to the fourth minus x cubed plus x squared minus 2x plus 4. The coefficient for x to the fourth is 1. Modulo 3, that's 1. For x cubed, it's negative 1, which is congruent to 2 mod 3. For x squared, it's 1, which is 1 mod 3. For x, it's negative 2, which is congruent to 1 mod 3. And the constant term is 4, which is 1 mod 3. So our new polynomial is f bar equals x to the fourth plus 2x cubed plus x squared plus x plus 1. Now the prime ideals of the ring z3x modulo f bar are generated by the irreducible factors of f bar. We need to factor this polynomial completely. Let's check for linear factors by plugging in the values from z3, which are 0, 1, and 2. F bar evaluated at 0 equals 1, which is not 0. F bar at 1 is 1 plus 2 plus 1 plus 1 plus 1, which is 6, congruent to 0 modulo 3. So x minus 1 is a factor. F bar at 2 is 16 plus 4 plus 2 plus 1, which is 39, congruent to 0 modulo 3. So x minus 2 or x plus 1 is also a factor. Since both x minus 1 and x plus 1 are factors, we know that their product, x minus 1 times x plus 1 equals x squared minus 1, is also a factor. We can now perform polynomial division to find the last piece. The division gives us f for it equals x squared minus 1 times x squared plus 2x plus 2. The linear factors are already irreducible, but we need to check if the quadratic factor x squared plus 2x plus 2 is irreducible. We can do this by checking if it has any roots in z3. 0 squared plus 2 times 0 plus 2 equals 2, which is not 0. 1 squared plus 2 times 1 plus 2 equals 5, which is congruent to 2, not 0. 2 squared plus 2 times 2 plus 2 equals 10, which is congruent to 1, not 0. Since it has no roots, it's irreducible. The full factorization is f phi equals x minus 1 times x plus 1 times x squared plus 2x plus 2. We've done the hard part. We found the irreducible factors of the simplified polynomial. Now we just need to lift these back to our original ring R. The prime ideals in R that contain I equal 3R are generated by the image of 3 and each of our irreducible factors. The generators are 3 in x minus 1, 3 in x plus 1, 3 in x squared plus 2x plus 2. So the three prime ideals are P1 equals 3x minus 1R, P2 equals 3x plus 1R, P3 equals 3x squared plus 2x plus 2R. And that's our final answer. This problem is a perfect example of how abstract algebra helps us simplify complex structures. By using isomorphisms, we turned a difficult problem into a straightforward factorization problem. If you found this explanation helpful, be sure to hit that like button and subscribe for more math content. Thanks for watching.